Welcome to our first of two keynote speakers. This is Professor Lorelei Koss. She's at Dickinson College under normal circumstances, but she's up at Colby College in Maine. And she's going to talk to us about differential equations with the arts, music, and literature. Everybody knows about mathematics and, the movement to match mathematics and this is a movement to match differential equations and she's written several articles on this. And when I asked her to come, she was very gracious and said she'd be more than happy to do that. So I'm turning the floor over to Lorelei.
Well, thank you all very much. I appreciate you coming and really excited to give this talk. So the background of my interest in this subject goes back a long while. In the United States, there is, we offer a lot of courses called Mathematics in the Liberal Arts. And I'm actually teaching one right now at Colby. And the purpose of those courses, they're usually populated by students who didn't really enjoy math in high school, sort of the typical algebra, geometry, trigonometry, pre-calculus, calculus. And, it's also common that students have to take some type of math course in college in the United States. I realize that that's different in other countries. And so we've developed many books and many courses to try to entice those students into our classes and to try to help them appreciate mathematics by teaching interesting applications and trying to engage them in mathematics. And so my interest here was, I read an article, and I'll talk about the article in the talk, and it made me think, could we go in the other direction? Could we look at using mathematics to entice students who love mathematical ideas to think about topics in sort of the arts and humanities broadly construed? And so that's what got me going here on this topic. So initially, I'd like to engage students in a differential equations course to think about topics in the arts and humanities. And so I wanted to try to come up with sort of a toolbox of activities that I could use to do that. I also thought that this would help students in that it would give them different tools to approach works of art. So, sometimes we see students in math classes, they love math, they love science, and they just haven't taken very many classes in the arts and humanities. And so they don't really have the tools to examine those works or to talk about those works. And this is a way that they can use things that they know to sort of start investigation of topics in the arts and humanities. And I'm by no way suggesting that this is sort of the best way to investigate the arts and humanities. It just gives students something to start with. Now, some of these applications are using standard traditional differential equations models that are covered in sort of every textbook and just applying them to an entirely different system. And so that is nice because we're not having to add extra material to a differential equations course. We just sort of add a homework problem or add an application to something that they're already studying. And I also just think it's very fun. So that's another reason that I like this topic is I just really, really enjoy topics in the arts and humanities and thinking about them from a mathematical perspective. The talk today, I'm going to give sort of an overview from 30,000 feet. When I've talked about this, these papers before, it has been to maybe general mathematical audiences. So the people in the audience maybe haven't looked at a differential equation since they were in grad school or undergrad. And so in those talks, I would give a lot of background about the actual models themselves. And I'm not going to do that here. I will put the models up there, but I think that everyone in the audience can sort of go and read a paper and understand the model. So I'm not going to go into the details about the models. I'm really going to just give you a brief survey of some of the ways that we can apply differential equations models in a differential equations in a differential equations class. Some of these models are silly. Some of them are really deep and powerful. So you just have to sort of pick and choose the things that you think are interesting and you think might work. Okay, so my title is, I didn't want to put all the words in the title, but what I'm going to do today is try to connect some differential equation models to topics in the visual arts, music, dance, and literature, poetry, and film. So very quickly and not in a whole lot of detail. All right, so I'm going to start with a very basic model, which is nice because you can introduce this early on in a differential equations course. And that's the topic of string art. So what I've seen is that this idea was credited to Mary Evers Boole in the 19th century. Here is a color photo from a 1906 publication that was talking about her work. And so here is what Boole said. Why did she start doing this? Well, she basically started a sewing project, and you were supposed to sew holes around the edge and go ahead and make a little pocketbook. And she didn't want to do that. She got bored. And so she just all of a sudden started lacing across the middle. So she wasn't following the directions, but she ended up seeing something very, very cool mathematically. So she saw these curves popping up in the lines of her sewing project. And in fact, you could buy cards that were laid out the correct way to make these cool designs. And so here is an advertisement of the Boole sewing cards that you could buy. I've never actually seen these. It would be very cool if someone had access to them. I don't know if there are any that are still around, but you could just purchase these things if you were interested in doing this at home. Okay, so the idea behind an envelope is that even though all the pieces of string form straight lines, what the human eye see is a curve. And the curve is coming through points of intersections of the tangent line to the tangent lines to the actual curve, which is the envelope. So like I said, this is a very simple differential equation. You can introduce it right at the beginning of a beginning differential equations course. If we look at the differential equation dy dx squared minus 4x times dy dx plus 4y equals 0, we can see that every line of the form y equals 2tx minus t squared for any real t is a solution. And so those tangent lines are always, or anything in that family of lines is tangent to a parabola. And so this is actually a kind of a fun project that you can do with students. So this is something I actually started during COVID when I was teaching on Zoom, and I gave every student a particular line in this family, and we used the drawing feature in Zoom, and they all had to draw their line on the graph. And then we could see if they were good at drawing the lines, if they were accurate at drawing the lines, and that did take some practice, we could see this parabola pop up. And so it was a way to sort of do something that I would do in the classroom online. And I've done this in the classroom as well, where they can just use all the different pieces and it will pop up that you have this parabola. So it's very cool. What does that have to do with art? Here is, so I'm going to show you the sort of a collection of works of art that are using these ideas behind envelopes to create the piece of art. So Sue Fuller was an artist. She started making these string art pieces in the 1940s. And here is a beautiful representation of it called String Composition T220. Her work is in the Smithsonian, in the Whitney. She's been shown at MoMA, at the Tate Gallery in London. And she has some really, really beautiful artworks that are just created from straight pieces of string. A more contemporary artist, Megan Geckler. So this is from, she was doing this work in the early 2000s. And you can see this is a big shipping container where she used, these are like pieces of plastic, technically thin pieces of plastic that she has strung up to create kind of these beautiful shapes that you can sort of walk into. Envelopes have also been used in architecture. So this is a print out of a book from 1905 called Modern Buildings, Their Planning, Construction, and Equipment. And the instructions are talking about ways that you could build an arch that actually forms a parabola. So you lay out your lines, you number them, you connect them up in the order directed, and you can use half of that curve for one side of your arch. And so this is sort of a way that architects could use string art to construct a parabolic arch as a support system for their building. Here is a bridge designed by Santiago Calatrava. So these white strings are actually the support cables on the bridge. And so obviously when you're designing a bridge, you have all these structural forces. So those are sort of, you would use differential equations to make sure that your bridge is stable. But what Calatrava did was actually use the support strings and lay them out in a particular way so that first of all, they supported the bridge. And second of all, they formed an envelope when you look at the bridge from certain angles. So this is the Margaret Hunt Hill Bridge in Texas. Yep, in Texas. And then he also has the Bridge of Strings in Jerusalem. So in this one, the photo's a little bit better. You can really see that envelope popping up there from the support beams. This bridge has 66 steel cables, and Calatrava talked a lot about how he designed this bridge intentionally to have that sort of beautiful shape pop up and for the bridge to be stable, which obviously is an important criteria as well. All right, this is just a fun application of string art. So this is a kind of jewelry. The earliest mention I can find of it is from the 1980s. It's called Peruvian string art earrings because I think the first article that I read about it said that the author saw these for sale at a street fair in Peru. Now you can find them all over the place on Etsy. So it's sort of easy to buy these earrings, but they're designed again with just straight pieces of wire that are laid out in a way to make those beautiful curved shapes. Okay, so envelopes, we have lots of applications from art, architecture, jewelry, and sort of if you just go look around, there are lots of other examples as well, where you can look at artists who are using these types of ideas in their exhibits. Okay, so let's move to another application. This is a story that was published in 1638 called The Man in the Moon. And the story describes a situation where the man ties a bunch of swans to a contraption and has them fly him to the moon. And so you can see the title page and the picture there, the illustration of the swans. And you'll notice in the picture, the swans are heading directly towards the moon in the picture. And so that's the setup of the story, that the swans are flying at a constant rate and they always fly directly at the moon. Now, one thing that's kind of funny about this is many of my students have never read a story in sort of older English with all the misspellings. And so they seem to have a lot of fun with trying to figure out what is the story exactly. Not many hours after the departure of that devilish company from me, my Ganses began to bestir themselves, still directing their course toward the globe or body of the moon. So heading off to the moon. So Samosin actually went through and did an analysis of the mathematical accuracy of this story. So how accurate was it to actually predict how long would it actually take the swans to actually get to the moon? So again, the mathematical object here that we're looking at is called a pursuit curve. So as they take off from Earth, you can see the Earth is at the center, the moon is all the way to the right in this picture, and the swans start flying directly toward the moon, but the moon is moving. And so as the moon moves, the swans have to continue to head toward the moon. And so they're sort of they're pursuing the moon there. Here is the model. We're letting the point at the center, 1, 0, be the original position of the swans, and the moon, the swans are at the origin, the moon is at 1, 0, and x of t, y of t is the position of the protagonist or the swans at time t. And so you can model the path that the swans fly by this following system, okay? And so you need some units that the swans travel, and you need a distance for the Earth to the moon, but you can go ahead and solve that problem using sort of standard differential equation, and you're just applying it to this sort of bizarre story back in the 1650s. All right. The next example is a complicated one in the sense that it doesn't necessarily appear in a first semester undergraduate textbook. Now, when I teach differential equations, I often have physics majors in the class. So even though it's a first semester differential equations course, they have often seen the wave equation before. They've just seen it sort of informally as a physics application. And so you can use the wave equation to model sound of stringed instruments. Okay, so I'm not going to go into all the details of the model here, but we imagine that the string is fixed at the two endpoints, and you pull up in the center of the string, or you pluck the center of the string, and you can model the movement of the string, and that is giving you a model for the sound of the instrument. Okay, so the application to guitar music, if you're just saying, can we make a sound, that is sort of a straightforward application. James Hughes actually looks at a couple of different applications of the wave equation to classical guitar. And so what are some of the, so I'm not a guitar player, but what are some of the ways that classical guitars are played? Well, you can vary the tone by dampening the guitar string at a certain point. And so you can model how that changes the wave equation. The other thing you can do is change, you can produce sort of mellow or metallic tones by plucking the string at a different position. So you could pluck it close to the fingerboard, or you could pluck it close to the bridge. And these are techniques that are used frequently in classical guitar performance to produce a different sound. So you're not just playing the notes that are written on the page, you're playing them with these modifications. It's used a lot in classical guitar when you have maybe one phrase and then you want to repeat that phrase, but you want it to sound different. And so you would use these techniques to come up with a different sounding echo effect when you repeat the material. And you can hear this kind of music. Really, it occurs a lot in classical guitar performance. So here's one example where you can sort of hear how these, Peter Fricker's Paseo is one example where you can hear this, but it's a very, very common technique in classical guitar. Now, the wave equation can also be used to model sound, even if you don't have strings on your instruments. And so there's a very nice paper by Rachel Hall and Kresimir Josic, which uses the wave equations to model different kinds of instruments. So here's a picture of a willow flute. It's got no strings in it. It's just carved from a willow branch. It's common in sort of the Nordic countries. Or maybe it came from the Nordic countries. And you can also use the wave equation for drums and bells. And they also talk about some three-dimensional instruments like the marimba, the glockenspiel. And so this is a nice paper. It's not, like I said, it's pretty advanced because the wave equation, you typically need to understand information about partial differential equations to look at that. Now, I did have a student who took undergraduate, sort of ordinary differential equations from me her junior year. And she was also a dual math physics major, and she was also a dancer. And so she, as part of her senior project in dance, choreographed a piece based on information from the wave equation. So this is one of the really fun things about including these ideas in the courses that I teach, is that every once in a while you'll have a student who takes something and really runs with it. So she found one piece of music that had 3 different performances. And so she used GarageBand to view the waveforms. So the waveforms, there's sort of what you're hearing in your ears. And there's also, if you use GarageBand, there's sort of a visual application of the waveforms as well. And so what she did was use what she was hearing and what she was seeing to choreograph a piece. And so here are the 3 waveforms that came through GarageBand, the 3 versions that she had. And you can see maybe for the second version, there are sort of big, strong, sharp peaks. And so when she choreographed her piece, the movements were big and strong and dramatic. When you looked at the third example, the orchestral piece, you can see that the waveform is very short and quick. And so she was using movements there that were very short and quick. And so here is a performance that they gave at Dickinson, the dance company gave. And so you've got the dancers, they're doing their movements, and it's hard to see in this picture, but on the screen behind the dancers, you can see the actual waveforms as well. So the audience members can sort of hear the music, sort of see the dancers move to the music, and they can also see how the movements mimic the actual waveforms of the equation too. So this was really, really interesting and fun. Okay, so wave equations, we had sort of the sound, we had the way you can perform on a stringed instrument, and then we had some dance choreography that were all coming out of those. Okay, jumping to the next topic, mathematical chaos. So there are, whoops, sorry, okay. So there are lots of pieces of art that are inspired or use some type of chaotic behavior. So here's just a classic one, the Lorentz system. It's a system of 3 differential equations. I drew a picture with some certain parameters there. The Lorentz system, it both exhibits chaotic behavior, and it also has an attractor that is sort of sucking things in. So I'm going to run through a bunch of arts and humanities topics that are inspired by mathematical chaos. Okay, so first is in music composition. So Rick Bidlack used these Lorentz equations to compose a musical piano piece. And the way that he incorporated the Lorentz equations was he used X, Y, and Z, those 3 variables, to represent frequency, loudness, and the duration of each note. So back to this equation, sort of the path of an orbit was determined by this Lorentz system, and that also determined the music that came out. There was a staging of Marisol at Southern Illinois University. Chua's oscillator is another example of a system that exhibits chaotic behavior, and they were using music inspired by Chua's oscillator to sort of highlight the setting. So the music was very dissonant and sort of set the scene for post-apocalyptic New York City. Another group, Joshua Bradley and Elizabeth Stewart, have choreographed a dance using lots of mathematical ideas. So symbolic dynamics, rigid body mechanics, computational geometry, graph theory, statistics, computational linguistics, and a chaotic system of, there we have it, ordinary differential equations. So I'm not expert in all of those fields. I certainly don't know what they did, but it is an example of how ordinary differential equations are inspiring choreographers. We can see ideas from chaos, particularly the idea of sensitive dependence on initial conditions, coming out in literature as well. So here's a quote from James Joyce's Ulysses. T.J. Rice pointed this out, that this little passage describes a situation where the idea from sensitive dependence on initial conditions is related. So the striking of the match determined the whole aftercourse of both our lives. So that one small change affected their whole lives. There's another example here from Ray Bradbury's A Sound of Thunder. This was a short story written in 1952. I assign this short story every time I teach either differential equations or dynamical systems because it's short and the students really seem to love it. The idea here is it's sort of a time travel story, and the big picture is a group goes back in time, they make a teeny tiny little change while they're there, and it ends up really influencing what they see when they come back. So here's a quote: a dead mouse here makes an insect imbalance there, a population disproportion later, a bad harvest further on, a depression, mass starvation, and finally a change in social temperament in far-flung countries. This is an easier read than James Joyce. I think James Joyce is interesting, but that's a challenging assignment. They enjoy Ray Bradbury. Okay, now I'm going to jump to another topic, the 5th topic, which is the 3-body problem. This was a problem that was originally formulated by Newton when he studied the motions of the Earth, Moon, and the Sun. So how are those three celestial objects interacting with each other? And there's a special case called the Pythagorean three-body problem that dates back to 1893. And you can use numerical techniques to find solutions. So the idea, the three-body problem, is you still have three bodies, but you're going to make their size, you're going to make their mass 3, 4, and 5, and you're going to start them on the vertices of a 3, 4, 5 right triangle. Okay, so it's a simplification. You're starting from a very prescribed situation. Okay, so you're starting them from rest, and then they're going to move based on Newton's laws of gravitation. Okay, so we've defined some R0, R1, and R2, and then you can describe the motion of the particles as a system of 3 differential equations. Okay. All right, so here's just a picture of the setup. The left-hand side shows the 3, 4, 5 right triangle, mass 3, 4, and 5. And the right-hand side shows a simulation. So this was some Mathematica code written by Michael Trott, and you can see the movement of the 3 bodies as time evolves. Okay, so there were some choreographers who used this idea to create a dance piece. So it was collaboratory. It used a choreographer, an astronomer, 3 dancers, a musician, and 2 experts in technology. And the idea is that they had the 3 dancers. They were trying to move in a way that mimicked the motion of the particles in the 3-body problem. And they were using that to explore feelings of longing, connection, and isolation as they moved close to each other, and then as they moved far apart from each other. And they used an LED. Each of the dancers wore an LED, so you could sort of see the lights move, and then they would project those LEDs onto the screen behind the dancers. And so you could also see sort of a 2-dimensional version of their movement as well. So the 2-dimensional version would look like the graph in this picture, just projected onto the screen. And you could also see the dancers moving in 3 dimensions as well. Okay, they used to have a video up online, and it's not available anymore. So fortunately, there is a photo of sort of the projection of the paths that they take, but I think the video is, the problem with the dance performances is typically you can't see any videos. And so it's a little bit of a struggle to sort of see the artwork in progress there. All right. The 6th application are linear systems. This was the first article that I read that really inspired me to think about these ideas in more detail. So Stephen Strogatz wrote an article where he was using a linear system to model the love affair of Romeo and Juliet. So R of T is Romeo's feelings towards Juliet at time T, and J of T is Juliet's feelings towards Romeo. And you can use this system and think about A, B, C, and D as representing different romantic strategies of the lovers. And that sounds very cold to think about different romantic strategies, but sort of how their interactions either make their love grow or make their hate and dislike for each other to grow. Now, surprisingly, most of my students have not read Romeo and Juliet. So this is another one where I actually go ahead and assign not the entire piece, but a subsection of it, so that they've heard of Romeo and Juliet. Some of them have seen a movie of Romeo and Juliet, but I like to actually force them to do a little bit of reading, because I think it's kind of great and important. And so I usually give them a reading, and then I have them do homework problems. So I give them sort of some parameters for A and B, some constants for A and B, and I have them go solve the system, and then I have them sort of interpret what happens in the long run. Do Romeo and Juliet end up being deeply in love with each other? Do their feelings sort of die off and they feel kind of neutral, or do they end up hating each other? And so this is, these problems are the classical problems right out of the textbook for linear systems. They're just characterized in terms of Romeo and Juliet. And students seem to really enjoy this. I actually do 2 assignments on this, because this chapter, when I teach it, is usually sort of a long chapter in the textbook. And I make them make up words to describe what's happening and sort of explain. And it's a real hit. Now, one of my students was also an Italian major, and she came to me after these assignments and said, I was assigned to do some research on Petrarch, and I found this paper that seems to be looking at the same ideas of Romeo and Juliet. So it's another example where students are kind of pulling ideas from their lives and bringing them back to me. And so Rinaldi has actually done a very similar, well, I should say very similar projects, because he looked at a lot of different works of art. But this was sort of the first one that I saw that my student brought to me. Rinaldi modeled the feelings of Petrarch towards Laura. So Petrarch wrote more than 200 poems about his feelings. And the collection, you can kind of read, sometimes he's very happy and deeply in love, like this selection here, thinks very, very fondly of Laura. And then there are times where he is feeling very sad and depressed about their future and his feeling towards her. So Rinaldi did something interesting. Well, obviously it's a much more complicated system than the Strogatz model of Romeo and Juliet. We have L is the strength of Laura's love for Petrarch. P is the strength of Petrarch's love for Laura. And then Rinaldi also uses this third variable, Z of T, to denote Petrarch's poetic inspiration. And so I like this because that third equation is sort of representing the creation of art. So the first 2 are really representing feelings, but the third one is representing the creation, poetic inspiration. And so you can see that dz dt equals negative g of z. So if you're just thinking about poetic inspiration in isolation, his poetic inspiration would be declining. But that positive HP means that his feelings toward Laura sort of change his poetic inspiration. So that's kind of a fun model. And again, you've got lots and lots of variables in there that describe different strategies and reactions depending on the poetry that's being written and their feelings towards each other. So it's a complicated model, but it's one that I think is interesting because of that third variable. So I labeled this 6.5 because I think it's very, very close. It's not really a different model than, it is a different model than Strogatz, but it's in the same theme. And there are a bunch of papers that are analyzing different types of relationships. So there's a paper on Elizabeth and Darcy in Pride and Prejudice, and Beauty and the Beast in Disney's Beauty and the Beast, and Rhett and Scarlet in Gone with the Wind. And so there's a lot out there. You don't just have to use Romeo and Juliet. You don't just have to use Petrarch. This idea has been done by a number of mathematicians. Okay, so the last example, I'm actually not going to write the differential equation up there. It's another dance performance, and this one I do have a video of, and so I wanted to show one. The creation of this is very interesting. So Moffat is an engineer, and he used an infrared camera to capture the dancer's movement, and then quickly used a computer simulation to compute velocity fields. So as the dancer is moving, the velocity fields are projected onto her and the screen behind her. And so her movements change the scenery. Okay, so I'm going to try now to show you. Okay, is there a video there? Okay, good. Okay, and so I'm just going to play, and you can see how her movements are determining the scenery. And I thought this is just so amazing and beautiful. And it's based on differential equations. Look at that. Yeah. Okay, so yeah, so you can find that, and we're not going to watch all 7 minutes of it. Okay, so let me go back to the slides. Okay, so very cool, beautiful application. There she is. I did have a photo of her in case the video didn't work. Okay, so like I said, these are sort of, if you're interested in either these particular topics, there are lots of topics I didn't talk about today, but here are 4 survey articles that I wrote that cover this type of project. And I wanted to finish real quickly. Obviously, you know, if you're interested in doing research in this area, you all can probably come up with awesome ideas on your own, but I did want to talk just real briefly about how could you use these in the classroom. So I've done different things. The first thing I tried was just to use them as a supplement to the class. So I would just, you know, give student links or to articles or videos, and students could either do it or not do it, depending on whether they were interested in this type of idea or not. And so this is very easy to implement. You just have to have a collection and post them on, you know, hand them out to the students. But, you know, some students did it and were very interested and would come in to talk to me. And then some students I could tell had zero interest at all. The other end of the spectrum would be just full integration of these models into the class. So sometimes I teach these models, I put them on homework, I put them on exams, and they're supposed to you know, be able to answer questions about humanities models just like they answer questions about any model. So they're sort of equal level to any model that I cover in the classroom. And I will say that this really depends on your institution. I'm fortunate to teach at a liberal arts institution, and I can put what I want in my differential equations course. You know, I have a lot of flexibility, let's say. Some of us teach at institutions where if you're teaching ordinary differential equations, what you teach is really prescribed, and you don't have a lot of room to move things around and sort of pull in unusual models. The other thing that's tricky about this is you can't just use the homework problems from the book because these examples are not in the book. And so you have to do a lot of work to come up with good homework problems and get them to the students. And the other thing that I've done that has also worked really well is assign projects. So the nice thing about projects is they don't take up much class time. And so you don't have to cut material out of your I see I have a typo in this. You don't have to cut people out. You don't have to cut material out of your syllabus necessarily. You have to build time in for them to work on the project, but I've had a lot of success with having them do presentations. And so I put them in groups, I give each group a project, and they come in and we have presentations on this, either just to the class or to a larger audience. And sometimes I've had some semester where I've had different types of projects, where some are in humanities and some are in the sciences. And I've also had semesters where I said, all of your projects are in the arts and humanities. You must do something and learn something from the arts and humanities. And so everyone will research an application in the arts and humanities and come give a presentation on it. Again, that depends a lot on your institution, whether this is a kind of thing that you have the flexibility to do, or the kind of thing that you don't. So I planned this talk to end a little early, hoping that there would be questions. So I am done with my part, and I'm happy to take any questions from the audience.
Well, first of all, thank you very much, Lorelei, for a packed session of goodies. And if you check the chat, several people have made some oohs and ahs. Frank Wattenberg has put in a number of additional sources. Oh. And it's obviously you have a passion for this. And I'm going to ask, are there any questions or suggestions or experiences anybody want to share? We do have time, lots of time. There's also a breakout with Lorelei after this on a smaller basis while other things are going on if you want. But yeah, Joe, speak up. Joe is a young faculty member of about 56 years of experience out in Los Angeles. So let's see what he has to say.
Okay, so I'm also, besides being an old professor at UCLA, I've been a musician all my life.
Okay.
And I've been thinking about how musical harmony is described by dynamic systems equations. Mm-hmm. And actually, I had some ideas about this a few years ago that I shared with a composer during a conference at the Disney Hall for the Los Angeles Philharmonic, and I don't remember what it was. So my more general question for you is, have you had any experiences or knowledge of how differential equations in any way have been involved in describing the harmonies that music makes? Now, that meaning simultaneous notes, musical harmony.
Yeah, I don't, and I'm hoping that someone in the audience does and will jump in for me, because I am not a musician, and so.
Yeah, I mean, the idea is that dynamics, and we understand what that means, and memory has a lot to do with that, meaning initial conditions, et cetera. That concept is used in music for its dynamical aspects in a big way, and that's where my specifics, ideas on this are kind of disappeared at the moment. I hope to get them back, and maybe with a little help from you and the audience, because the greatness of all music depends on all of the properties that you had described earlier, loudness, et cetera, frequency, et cetera. And all of those are described by differential equations. So, I mean, can be described by differential equations. So I'd like to hear more about how this has been used historically in research.
Yeah, no, my gut is that it's all going to go back to the wave equation, because the wave equation, sort of the different vibrations of the strings is what you're hearing. And so I think that in harmony, you're sort of taking two different wave equations and making them, I don't know, agree with each other, or making them sound good with each other.
Right.
Yeah.
Yeah, I know that if you listen to June Carter and Johnny Cash sing Jackson and We Got Married in Memphis, this harmony is just magnificent. Or if you listen to a Bach chorale, but if you go to a junior high concert, you know it ain't. So the question is, what is it that makes it good? And some people think no modern music is good because it doesn't give you that soothing feeling. And also, how do we drift into good harmony? I mean, sometimes a voice starts and it's drawn to the other. The alto is a little high and she will bring it down, to contrast the soprano. And so there's a lot of on real time dynamics, and then there's a lot of that's what the note says. But I think more than one note. The song "Sing Johnny One Note." That's not what I'm talking about, but more than one note is probably rich if we wanted to look. I think that's great. Thank you. I wanted to ask about collaboration, Lorelei. Have you ever collaborated with an art professor, maybe, or a musician coming to class, or you bringing them to some facility, or you just do most of this on your own? You obviously bring the literature in and you bring videos in, but have you found peer collaborators at all?
No, I have not found peer collaborators. I have to say that work that I showed with Katie Roy, who was a student, that was some collaborative work where she was coming and bouncing ideas off of me as a former student. But I haven't, I haven't sort of created any of these models on my own.
Okay.
Do you know of any website or repository that has resources for things like this? I mean, it'd be really wonderful to have. There's a lot of stuff out there, but it's scattered all over the place.
No, but because not everything, but most of what I know is in those papers, but that makes me think maybe I should make a website.
Cool.
Well, yeah, no, this was just all stuff that I found, just randomly, or people would send things my way. Some of the editors on the papers had suggestions when I was writing these papers, but no, I don't know of a good repository.
So Semiote itself, we're in this long transition period to CUBE's website, and we would be glad to host that kind of a website and draw people. The example I wanted to give is writing for audience. So I work with an English teacher, and we had students doing consulting work and building a differential equation for some purpose for a client that came to my class. And then the students had to write up something for a senior analyst and for the shop guy. And so I collaborated with my English professor colleague, and she had them talking about, when you write for this audience, you do this. When you write for that audience. So it doesn't have to be deeply embedded, but for example, maybe have an art historian talk about how you make a presentation about art. So the collaboration doesn't have to be so deep, but it brings them into your class, and you get to find out a new colleague. So
Yeah.
Well, thank you, Lorelei, very much. We appreciate. I wish I could play some fanfare, but I can't. And
Thank you.
Thank you.
Thank you. We're all appreciative. So we'll see you in the next session, maybe or maybe not. Take care.